Hi, everyone. Welcome to technical session 5 of ICFP 2020. My name is Richard Eisenberg. I'm principal researcher at Twig.io and a member of the ICFP program committee. This session will be streamed via YouTube, but is also available via Clouder. So those of you who registered, if you're on YouTube, please switch over to Clouder. You should have gotten a notification, an email about how to do so, and that will give you access to more interactive features of these presentations, including links to the question and answer sessions from the authors. So first up in this session, we have Joe Cutler, who will present how we can extract recurrence relations from functions for amortized analysis.
Hi, I'm Joe Cutler. I'm an undergrad at Wesleyan University in Connecticut, and this is joint work with my advisor Dan Licata and Norman Danner. So if I handed you this code for merge sort and then asked you to write down a recurrence for its worst case execution cost, you'd probably end up writing down pretty much exactly this expression right here. But the thing you did in your head to get there is actually pretty subtle. It required knowing things about the sizes of results of functions, like the fact that split splits a list in half, and abstracting lists down to just their lengths. And even more importantly, as a PL person, you might even have an operational semantics for the language that this function is written in that precisely defines the cost of program execution in terms of beta redexes or some other cost metric. And how do you know that this recurrence you wrote down has anything to do whatsoever with those formal costs? So, in other words, how do we make this informal process of recurrence extraction formal and ensure that it's correct? Well, at ICFP 5 years ago, the other two authors of this paper, and their co-author, presented an answer to exactly this question. And I guess rather than keep you all in suspense, I'll just show you what they came up with. So, recurrence extraction is formalized as a language-to-language translation. So given a term in some source language, we can translate it into a language that we call lambda C, which is a language whose terms are syntactic recurrence relations. Now, the overall idea of this translation, which we often call formal recurrence extraction, is to translate terms to output their evaluation cost, along with the size of the result. So, a term of type A in the source gets translated to a pair, consisting of the cost to evaluate that term, along with the resulting value, the size of the resulting value of type A. Now, this size translation that I'm talking about is essentially the identity on values, but except at higher type, where the size of a function is a recurrence in the traditional sense. So it's a function from sizes to costs and sizes. Now, the real meat of this recurrence extraction is the term translation, which is defined compositionally by recursion over raw syntax. So given a term in the source, we can just translate it to a term in lambda C. Now, if you're a monadically minded person, you might recognize all of this as being a monadic translation into the writer monad. And all of this helps motivate the definition of the size translation. Arrows in the source become Kleisli arrows in lambda C. So we've extracted recurrences from the source language into lambda C, and now we need to prove that this extraction procedure is correct. Otherwise, all of this is no better than just extracting recurrences the old informal way. So the first step here is to fix an operational semantics for the source language, which is indexed by execution cost. You can read this judgment as M evaluates in n steps to V. And then we prove this following theorem using a logical relation. So for any closed term M of type A, if M evaluates in n steps to V, then the extracted cost of running M is an upper bound on n, and also the usual logical relations value relation nonsense. But anyway, this theorem is the crucial step. It formally connects the operational cost model to the extracted recurrences. One important piece of the informal analysis that this translation doesn't take into account is size abstraction, like, say, analyzing a function which takes a list in terms of its length, or a tree function by depth, or something like that. Now, we do this abstraction using a denotational semantics from lambda C into partially ordered sets, and this means that the objects that we get out are the standard objects you'd recognize as recurrences. You can compute closed forms and asymptotics and stuff like that. Okay, that was a lot of technical detail, I acknowledge that, but luckily all this has all been done before. And in the years since this technique was developed, it's been employed to formalize recurrence extraction for increasingly realistic languages, from the simply typed lambda calculus to inductive types, all the way up to PCF and ML-style let polymorphism. But all of this prior work is limited in the kinds of analyses they can handle, only ever worst case cost analysis. And in many cases, worst case cost analysis simply isn't enough to get tight bounds. And a technique like, say, amortized analysis is required to get better bounds. And so in this work, we extend the recurrence extraction technique to handle amortized analysis. So in the paper, we go over two standard examples of amortized analysis to demonstrate the effectiveness of our technique. And the first is a simple binary counter, and the second is splay trees as presented in Okazaki. The splay trees are notable because they aren't really well handled by automated amortized analysis techniques such as resource-aware ML. And since the analysis of splay trees is really complicated, I only have like 10 more minutes, I'll use the binary counter as a running example to motivate the way that we made our paper's main contribution. So consider a binary number represented as a list of bits with the least significant bit at the head. We can define an increment function in the standard way. Note that if the least significant bit is 0, the increment is constant time, but if the least significant bit is 1, we have to make a recursive call down the tail. Then we can define a set function which just sets the counter to a natural number value by looping increment n times. So here are the recurrences that you'd expect to get from these functions using the informal method. By the way, for the rest of the talk, we'll fix the cost model that cons operations are the only costly operation, and they each incur one cost. So these two recurrences here solve to t-inc being linear and t-set being n log n. But this actually isn't a tight bound for set, it's actually linear. Intuitively, this is because the constant time case of the increment happens way more often while you're looping, but you have to take the max between the two non-empty branches when you extract the recurrence, which makes it look like increment traverses the whole list every single time. And unfortunately, this is exactly what the prior work in formal recurrence extraction would do to this example. To motivate some stuff down the line, let's take a look at how that would go. So we can take our increment function written in the source language and pass it through the recurrence extraction translation to get a function into a pair C cross, which computes the cost of running increment along with the size of the result. Now, the first component of this pair is the important one. It's the execution cost. So I'll just write that with the subscript C. Now, this syntactic recurrence that you get out is exactly what I hope you'd expect. The key case is when the least significant bit is 1, it costs 1 for the cons, plus the cost of recursing down the tail. Now, after this, we use the denotational semantics to interpret this recurrence as a map between posets. Most importantly, we interpret the bit list type as the natural numbers, which abstracts a list to its length in the traditional way. Now, the monotone maps of posets we get in the semantics represent the exact same loose bounds that we talked about before. If you carry it all through for set, you still get n log n. So, we've seen how the previous work comes up short. Now let's take a look at how the amortized analysis of the binary counter actually should work to help inform how to change the recurrence extraction to get the tight amortized bounds we're looking for. So here's a quick refresher on amortized analysis for those of you who've forgotten about what the big deal was since you last learned about it. So amortized analysis comes in a few different forms, but all of them boil down to essentially smoothing out cost across program execution so that when you analyze repeated executions of the same function, they don't all look like the most costly one and instead look like, say, the average one. And the approach to amortized analysis that we take in the paper, which is usually called the banker's method, is to maintain an invariant of imaginary credits on the nodes of a data structure. So these credits incur a cost to create, but then you can spend them to decrease cost. And by passing these credits around the program, you can rearrange costs. The credit invariant for the binary counter is that we keep 1 credit on each cons cell, which holds a 1 bit. So here's an example to illustrate how this works. We start with an empty counter with no credits, and then the first increment flips the first bit, and we spawn a credit to put on the 1. Total amortized cost here is 1 cons plus 1 created credit equals 2 amortized cost. And then the next call to increment flips the first bit from 1 to 0 and the second bit from 0 to 1. And then to reestablish the credit invariant, we spawn a credit to put on the new 1 bit, which incurs a cost of 1, but then that's canceled out by spending the credit which used to be on the least significant bit. Again, total 2 amortized costs. This is the essence of the analysis, and you can convince yourself that in every case, the amortized cost of increment is 2. So in order to do this kind of analysis by recurrence extraction, we need to make these credit policies expressible in the source language. So to that end, we extend our source language with credits to make a language that we call lambda A. So lambda A internalizes everything you need to express credit invariance in your code, and it comes in 3 main parts. So first, we need to be able to track the credits using the type system. So this new typing judgment says that M is a term of type A in context gamma, which can use up to C credits. Now, since we don't want credits to be duplicated and then the same credit spent twice, the type system is affine, which means that variables can be used at most once. So next, we need to be able to attach these credits to terms, like, say, the elements of a list. And to do this, we add a modality to the language. The terms of type bang CA are morally terms of type A that carry C extra credits. And the intro and elim rules for this modality are actually pretty intuitive. The intro rule says that if we have a term M of type A and we have C extra credits lying around, and we don't need to construct M, we can just attach them to M and get a term of type bang CA. And the elim rule says that if we have a term of type bang CA, we can peel the credits off the term and allow them and the value to be used in a continuation to make more stuff. So finally, we need the ability to create and spend credits, of course. And the create rule here says that if we have a term which uses A plus C credits, we can simply create C of them. And dually, the spend rule says that if we have A plus C credits, we can spend C of them, and then use a term which only requires A credits. Now, all of these changes I just described are completely local to Lambda A. We don't change the recurrence language at all. It's still fully structural and has no modality. So, we've extended the source language with the features that let us formally specify these credit invariants in our code. Now let's take a look at how the binary counter example would actually get encoded into this language. So, in Lambda A, we redefine the bit type to be unit plus bang1 unit. A bit is either in left of a unit, which represents 0, or in right of a unit with 1 credit attached, which represents 1. And then the code for increment has the exact same behavior as before, it just maintains the credit policy. If the list is empty or has 0 as the least significant bit, we create a credit and make a 1-bit value by attaching that credit to a unit value and then returning that as the least significant bit. And if the least significant bit is 1, we detach the credit using transfer, spend it, and then make a recursive call on the tail and cons a 0 onto the result. So, all good, Lambda A can express the credit policy that we were looking for, but now we need to actually extract recurrences from it. But the recurrence extraction for Lambda A is actually quite simple. So let's briefly recall that the recurrence extracted from a term consists of a pair of the cost to compute the term along with its size. So since creating A credits incurs a cost of A, we just add A to the extracted cost, and dually we subtract A from the cost component when we spend. Now, since the credits, as I mentioned earlier, aren't present in the recurrence language, the extraction has to erase the modality in its corresponding form. So save gets erased completely and transfer gets turned into a len. All good. So now that we have the recurrence extraction in place for Lambda A, let's extract terms for recurrences for the binary counter, solve them, and hopefully get the type bound we were looking for. So above line here is the term for inc that we wrote earlier, and below I've written the cost component of the recurrence you get in Lambda C for this term. So when the argument to this recurrence is empty or has 0 as the least significant bit, increment costs 2. 1 from the cons, 1 from creating the credit. When the least significant bit is a 1, the cost we extract is simply the cost of the recursive call. Now, why is this? Well, we do one cons operation, which costs 1, and then we spend a credit from the least significant bit, which subtracts 1. So we're just left with the cost of the recursive call down the tail. And it's super easy to see that this function is 2 everywhere, and indeed the monotone map of posets that it denotes is in fact the constant function 2. So carrying this all through for set, we get that the corresponding mathematical recurrence is order n as desired. So, we have a recurrence extraction procedure that extracts tight bounds for amortized analyses, and the final step here is to prove a theorem like the bounding theorem for prior work, which connects these recurrences to the operational semantics. And similar to how we did it in prior work, we first define a big step operational semantics for Lambda A, but this time indexed by amortized cost. So this judgment reads that M evaluates to V with n amortized cost. Then we use a logical relation to prove the same bounding theorem as before, but this time the cost we're bounding is an amortized cost. But the crucial consequence of this theorem is that for closed terms, the amortized cost that we get for the recurrence is a bound on the actual execution cost. And so, for example, the set program isn't just linear in this strange cost metric where we can subtract and add arbitrary costs. It actually does a linear amount of cons operations. So in summary, we formalized a process of doing amortized analysis by recurrence extraction. Given an amortized analysis of a data structure, such as a binary counter or splay tree written in lambda A, we can automatically extract correct recurrences into lambda C. This extraction procedure has been proven correct and is expressive enough to handle non-trivial analyses like splay trees. Thank you very much.
Thanks, Joe. Now in both the New York and Asia time bands, you should be able to click a link in the sidebar in Clouder to be able to access the Q&A sessions. Okay, our next talk is featuring Arthur Charguéraud about separation logic for sequential programs.
Separation logic was introduced in the early 2000s. Since then, it has had tremendous success at program verification. I believe that today, the ideas of separation logic deserve to be taught much more widely. For this reason, I've been working on a course on separation logic. The course focuses on sequential programs. Concurrency is interesting, but it's much harder. The course is written in the style of the Software Foundation series, where every definition, every lemma, and every exercise is formalized using the coq proof assistant. The course covers modern features of separation logic. These are features that were not present in the original papers on separation logic, but have, since then, proved very useful for developing practical tools. The third contribution of this paper is an extensive related work section, which I believe nicely completes Peter Horan's survey, which was published last year, by focusing specifically on the contributions to mechanized presentations of separation logic. My course is organized in 10 chapters. The first 3 chapters focus on basic features of separation logic, such as heap predicates, triples, entailment. The next 3 chapters focus on the presentation of reasoning rules, either in the form of triples, in the form of weakest preconditions, or in the form of characteristic formulae, which are a form of weakest precondition generator. The remaining chapters focus on more advanced features, such as the magic wand, the treatment of affine predicates, and language extensions, such as records, arrays, loops, or NRE functions. Let me take a few minutes to explain how the course is set up at a very high level. Traditional courses on separation logic consider while loop language. I consider instead, like other colleagues before me, an imperative lambda calculus. This choice leads to major simplification. The fact that there are no mutable variables leads to an elegant statement of the frame rule without any side condition. At the same time, the use of a lambda calculus means that every term produces a value, and this leads to a minor complication, the fact that postconditions need to describe not just an output state, but also an output value. Concretely, where preconditions are of the type heap to prop, postconditions are of type value to heap to prop. The standard operators, such as a star, a magic wand, or entailment, thus need to be extended to a form that operates on postcondition. These are marked with a little dot symbol below the operator. The semantics is described in the standard way as a call by value, substitution-based, big step style semantics. The choice of a big step semantics is well suited for reasoning about total correctness of sequential programs. It makes the proof simpler. Both the syntax and the semantics are described in standard ways following the style of the presentation of the prior Software Foundation volumes, which will make it easy for students to follow. Separation logic is presented in a shallow embedding. This means that the core heap predicates of separation logic are defined as coq functions from heap to propositions. Entailment is defined in the standard way, as simplest possible way, as pointwise entailment. The remaining operators are encoded in terms of these core operators. All the details I will just refer to the course. Triples are defined in 2 stages. First, a hard triple, HTQ, asserts that for any state S satisfying the precondition, the term T terminates on a value V and an output state S prime that, together, satisfy the postcondition Q. A separation logic triple, HTQ, is defined by quantifying universally on a predicate H prime that describes the rest of the world, and asserting that the triple made of H star H prime and Q star Q H prime makes up a valid R triple. The standard technique of baking in the frame rule leads to simple proofs for the structural rules, such as the frame rule or the consequence rule. I'd like to take the rest of the talk to present 4 features of modern separation logic, which I believe should be to interest of every ICFP researcher. Let me begin with a ramified frame rule. The frame rule, in its most standard statement, is almost never applicable. Indeed, you need both the precondition and the postcondition to syntactically feature a star H2. Thus, in practice, one will typically use a combined rule that integrates the rule of consequence and is stated as follows: to prove a triple HTQ derivable from a triple H1TQ1, one has to show that the precondition H decomposes as H1 star H2, and then shows that the postcondition Q1, when extended with H2, recovers the postcondition Q. H2 can be computed as a difference between H and H1. Computing this difference can be well automated in the simple cases, but if H contains existentially quantified variables, it can be quite tricky to figure out whether these corresponding variables should get quantified in H1 or in H2. The ramified frame rule avoids this problem altogether by removing the need to introduce H2 in the first place. It reformulates the premises as a single entailment. H entails H1 star some predicate such that when augmenting Q1 with it, we obtain Q. The operator at play here is the magic one for postcondition. Without going into further detail, let me just point out that the ramified frame rule has proved very practical for developing practical tools. The second point I'd like to focus on is the weakest precondition presentation of separation logic. Just like in all logic, weakest precondition is a key ingredient, but what is the definition of WP in separation logic? And what is a statement of the frame rule in weakest precondition style? So WP, just like in all logic, can be defined as an equivalence between a triple HTQ and the entailment from H2 WPTQ. This equivalence is not quite a definition. There are 2 definitions that are can be considered. One is a low-level definition, working in terms of heaps, and another one is based on an encoding using the operators of separation logic. The weakest precondition frame rule can be read as follows. If I own a resource, a state, in which I can execute the term T and obtain the postcondition Q, and separately I own a piece of state described by H, then altogether I own a piece of state in which the execution of T terminates and produces a postcondition described by Q extended with H. Interestingly, the weakest precondition frame rule can be combined with the ideas of the ramified frame rule, leading to the rule shown at the bottom of the slide here. This rule subsumes all of the structural rules of separation logic. The third feature is a mixing of affine and linear predicates. A linear predicate describes a resource that must remain accounted for throughout the reasoning. It is essential, for example, to prove that every allocated data eventually gets deallocated, or every file open eventually gets closed. An affine predicate, on the contrary, describes a resource that may be freely discarded in the reasoning. Typically, this notion of affine predicate is a must-have for garbage-collected languages, which do not feature explicit free operations. So it is straightforward to set up a linear separation logic, and it is not much harder to set up an affine separation logic. But what is a simple way to set up a separation logic where both linear and affine predicates can coexist? I describe in the course a construction that is relatively simple, which relies on the introduction of a predicate, H-affine, that can be customized to define which heaps should be considered affine as opposed to linear. On top of that, can define the notion of affine heap predicates that characterize only heaps that are fine, and the notion of a affine top predicate, which characterizes any affine heap. The definition of separation logic triples can be generalized by introducing a affine top predicate in the post condition. Doing so preserves the validity of all the prior rules of separation logic and adds two additional rules. The first one asserts that any piece of precondition H prime may be discarded from the precondition provided that it's affine. The second rule allows to extend the postcondition with an affine top predicate, reflecting on the fact that it is fine to produce a postcondition that is bigger than the desired one. Fourth and last feature I'd like to describe is a frame-friendly rule for reasoning about loops. So consider, for example, an operation that traverses a linked list or traverses a tree data structure recursively. If this operation is implemented as a recursive function, one can invoke the frame rule around the recursive calls to forget about the cells or the parts of the trees that are passed by. On the contrary, if the operation is implemented as a loop and specified using a loop invariant, the loop invariant must describe the list segment of cells that have already been passed by, or worse, in the case of a tree, must describe the tree context associated with a path that has already been traversed. The question here is, how can we reason about syntactic loop construct as easily as a recursive function that will allow us to exploit the frame rule? So what we're trying to achieve here is essentially simulate an encoding of a while loop as a recursive function, but without introducing the overheads of an actual explicit encoding. The idea is to specify the while loop by relating the behavior, the state at the given iteration with the state after the last iteration. And such a specification can be established by induction, using Cox's induction mechanism, by applying the following unrolling rule, which essentially unfolds a while loop one iteration. This rule introduces a conditional, a sequence, and a recursive occurrence of the while loop. When reasoning about this recursive occurrence of the while loop, one may apply the frame rule to frame the parts of the list or of the tree that we are stepping over. So in the course, I described an example illustrating this proof technique and compare it with the proof based on the loop invariant. In conclusion, you can find on my webpage the paper, including its 8-page appendix, on all the course material, both in calc format and HTML format. This course is meant to be released soon as a volume of the Software Foundation series. I'm actually seeking for feedback, both from students and teachers, to further polish the material. So if you're interested, please get in touch with me, and I will be happy to serve as a TA for you if you're teaching the course. Thank you very much.
Okay. Thank you very much, Artur. He's now available in the New York time band for question and answer. And we'll take a brief pause to sync up with the advertised schedule. Now we have Aaron Stump presenting his strong functional Perl, Harper's regular expression matcher in Cedille.
Hello, I'm Aaron Stump, and today I'm going to present to you our strong functional Perl, Harper's regular expression matcher in Cedille. Harper's regular expression matcher is a continuation-based algorithm for regular expression matching, introduced by Robert Harper in his JFP paper titled Proof-Directed Debugging. And the basic idea of the algorithm is to decompose regular expressions. So you're going to dig down into the regular expression, building up a success continuation. If you detect a clash where the regular expression is asking for some character that's not there in the string, then you just return false. But if you find a character match, then you're going to invoke the continuation to keep processing the suffix of the string. And Harper's paper is, he called it proof-directed debugging because there's an interesting bug in the termination argument for this algorithm unless you use standard regular expressions. So your R star is allowed only if the empty string, epsilon, is not in the language of R. And here in this talk, we're going to enforce that syntactically using a type stdreg for standard regular expressions. And this is an idea we got from a paper from Dan Licata and his students. So here's a look at the implementation in Haskell. We're going to move to the implementation in Cedille in a little bit, but to start off in Haskell, so it's a continuation-based algorithm, so we have a type K for continuations. It takes strings to bools. They're going to take suffixes, tell us whether or not they match. And then there's a type match T for convenience that just says continuation goes to bool. So here we see the two central helper functions of the algorithm. There's match H, it takes a string and one of these regular expressions, and a continuation. Now, it's the first equation of match H, you see, if that string is empty, then we just return false, because these are standard regular expressions. They cannot match the empty string. Otherwise, we just split the string into its head C and tail C's, and we invoke this second helper function called match I. Okay, and here we see the semantics in the form of these standard regular expressions too. So match I, you can match no match regular expression that just says nothing's going to match, you just return false. There's match car with a character C prime, and then you check, does C equal C prime? And if so, that's the success case, and you invoke this continuation K on the suffix C's. And otherwise, you return false. For an OR regular expression, you just decompose and just check disjunctively the two parts of the regular expression. For the plus case, though, this is where the interesting termination issue comes up. So if we have plus R, we want to match R to see if it matches one time, because this is plus R, of course, being one or more matches. So we match it one time, and then in the continuation that starts out with lambda C's prime, we're going to say, well, let's try just calling the continuation K on C's prime. That would represent an exactly one match of R. But if that fails, then we want to go and we're supposed to recursively try the whole regular expression again on the suffix C's prime. So that's what I've got highlighted in red there. And the interesting thing about that, of course, is that the regular expression is exactly the same as we started with. Plus R, we just make a recursive call with plus R. So there's been no structural decrease here, which is quite worrisome for a termination situation. And then concat similarly decomposes and updates the continuation. So the problem of termination for this algorithm has been actually studied by a number of different previous works. You can sort of see the main problem right here in this little part that I pulled out from the code we were just looking at. And so we have match H that calls match I, and match I wants to call back to match H in this red highlighted call site there. But it's calling it with this C's prime. It's just a value it got from its continuation. It has no idea, the code, there's no obvious syntactic connection between C's prime and C's. So it seems that you need something like a proof that the length of C's prime is less than the length of C's or something like this. And in fact, previous works that tackled termination of Harper's regular expression matcher, some of them anyway, use dependently typed continuations. And in fact, one of these papers, a very nice paper I highly recommend by Beauvais, Krauss, and Sozo, raised this challenge that there seems to be no easy way to achieve the same effect without the use of dependent types. So in this Perl, we're showing Harper's matcher as a strong functional program in the sense of David Turner. So the idea is that we want, in strong functional programming, is we want to statically enforce termination of programs, but the name of the game here is you're only allowed to use the types of regular old functional programming, just polymorphic types. You can't use dependent types, you can't use size types, you're not allowed to use termination proofs or variants or metrics or well-founded orders. all that heavy-duty machinery of termination is not allowed in the regime of strong functional programming. And so we are happy to report that, in fact, you can do this example without dependent types. You can just use the toolbox of, well, advanced strong functional programming. So how can you do that? That's what we're going to talk about for the time we have here. And we're using our language Cedille for this. And so strong functional programming in Cedille. Cedille is a dependent type theory, kind of like Calc or Agda. And termination of programs is enforced by typing. But here, Cedille has some particularities that make it a bit different from Calc and Agda, and one of them is how termination is handled. So, and that's part of what we're going to have a little tutorial about in this talk. So in Cedille, when you're writing a recursive function, you're presented with something that we call a recursion universe. It's a typed interface for doing the recursion. Okay, so you get an abstract type R, that's what we're sort of thinking of as the universe, the recursion universe, and it has some operations on it that help you write your recursion. You're not allowed to make direct recursive calls in your code. You have to kind of go through this interface. And the language, though, Cedille provides special syntax for these recursion universes that pretty much hide a lot of the machinery and make it feel quite idiomatic way of writing recursive functions. So I want to emphasize, even though Cedille is this type theory that lets you do proofs and things like that, independently typed programs, here we're not using any dependent types or any of that kind of machinery. We're just using strong functional programming. Okay, so let's see how this works in several steps. So the first point, we're going to see the sort of Cedille's recursion universes. So we start off with something called a Mendler-style recursion universe, okay? And so this is kind of like the underlying interface, and again, Cedille provides sort of a little bit nicer surface language access to this interface, but this is the basic interface that we're relying on. So let's let f be a signature functor for a data type. So, for example, if your data type was list of A's, then your signature function is fx equals unit or A cross X, okay? So if you want to, suppose you're trying to write a function that's going to compute value of type X from your data type D. Then what the recursion universe provides you is this abstract type R I was mentioning. It's just some type. You have no idea anything about the type except what the interface gives you about it. The first thing it gives you is an eval function, R to X. Okay, and this is the function you have to invoke if you want to make a recursive call. You've got to call eval, but you can only call it on an R thing. You can't call it on just some random other D thing. And you're also given a subdata structure of type FR. In other words, you're given this little package that is presenting you the data that you have, except at the sort of functorial position, it's got the abstract type R. And so the key thing about this is that, and this goes back to this idea of Mendler-style recursion, is that you can only call eval on subdata, because the only things you have lying around of type R are the things that are hidden, presented to you in this subdata structure, and so that's the only stuff you can call eval on. So that ensures you are doing a structural termination, even though there's no sort of check about, is this variable I'm making a recursive call on somehow structurally derived from my input or anything like that. It's all done through the typing. Okay, so that's Mendler-style. Now, Mendler-style paramorphic recursion universe. So this is the next sort of step, presenting sort of a conceptual development of this idea of Cedille's recursion universe. So for computing X from data type D, now for paramorphic recursion, the universe gives you the same stuff you had before. The recursion universe has all these same pieces, but it also comes, as I highlighted here in black, with a reveal function R to D. So this unmasks R as really being D, okay? So, but notice you can't go the other way around. You cannot inject D into R. That would be totally unsound from a termination perspective, because you could just stick random values into R and then recurse on them. But here, you are allowed to sort of leave the recursion universe. You can sort of, wormhole out of there if you want to have some data D. And this is really important if you want to write efficient accessor functions like predecessor or tail or something. Now finally, what we need for the Harper's regular expression matcher is we need support for nested recursion. So you have all the same stuff we had before, except we change a little bit. The return type of your function now could depend on D. So you compute X of D from a data type D, and the reason that's really important to shift as I say below my bullet points there, from x of kind star to x of kind star to star, is that now the eval function, you can write an eval function that goes from r to x of r. And that gives you the possibility of seeing, when you return something from your recursive call, that it also has type r, and hence you could make a recursive call again on that. So a recursion is then allowed on values that eval has returned. So that enables a form of nested recursion, and the continuations are basically hiding a form of nested recursion. Okay, so let's take a look at how we do this in Cedille, Harper's matcher in Cedille. So the critical part about the nested recursion is here. So in blue, I've highlighted Cedille's syntax for indicating the abstract type R. If we're doing a recursion here, mu match, then mu is for the sort of kicking off a recursion. Then type slash match is R. That's the abstract type of the recursion universe. And the X, the type we're computing, here has to be given explicitly. Cedille can't quite manage to infer this for you. And it can mention this R. And that's just like XR or XD. Now we have a way of mentioning, we're indicating the functoriality of X. And X does have to be positive for this to work. And finally, where the eval function is conveniently called match. And so this looks very much like an idiomatic recursion. Now here we're doing something that would be tough to do in other type theories, where passing the recursive function match there to the helper function match I. But anyway, that match is the eval, and it has the type below. It takes in the abstract type R, which here is denoted type slash match, and proceeds. Okay, so that's sort of the setup for the recursion, introducing the recursion universe pieces that we then need to write this helper function and make that deal with that one nasty recursive call. So you can see I've highlighted it here. It's transliterated into Cedille code, but I hope you can sort of still make out the structure. We have a plus R case and that I've pulled out here. And we're going to make this recursive call to check one occurrence of R. And then when we make the recursive call, we're calling on match C's prime. And that's great. This match function is actually coming in to match I, as you saw where match I is invoked on my previous slide. The match function is coming into match I, and it's expecting type T, where T is actually just some abstract type. We really don't need to know much about it, except we can recurse on it. If you're looking at the type signature of match I at the top, we can recurse on it, and the suffix comes in at that type. And so when we call match of C's prime, match is expecting input of type T, and C's prime has type T because C's prime is the input to the continuation, and the continuation, as I noted there in blue, has type KT, which is T to bool. Okay, so to conclude, we talked about Harper's regular expression matcher, which uses continuations for a very elegant control flow that leads to complications for termination reasoning. And we saw a solution now using strong functional programming in Cedille. It's type-based. There's no fancy extra additions beyond regular types of functional programming. No dependent types, nothing like that, even though Cedille does support those separately. So we use this idea of a recursion universe that gives you a form of sort of type-based nested paramorphic recursion. And it turns out that Harper's matcher is just a perfect fit for this. It's very easy. We don't have time to wade through all the code, but it's really pretty much a direct port of the Haskell code because of the way that the abstract type for the eval function matches up perfectly with the inputs for the continuation. So thanks very much to funders, and I'd really like to thank the very dedicated anonymous ICFP reviewers who gave us outstanding, really above and beyond kind of criticism and help getting this into good shape, and Shepard Richard Eisenberg, and colleagues here at Iowa, and thanks to you for watching.
Great, thanks, Aaron. And now in the New York and Asia time bands, we have authors available for question and answer, so please follow the links via Clouder if you wish to join that. We'll take a brief pause until the next talk at 11:45 in the New York time band. Next up, we have Nandor Leaker, who will present Duplo, a framework for OCaml post-link optimization.
Hello, my name is Nandor and today I am going to talk about Duplo, a framework for OCaml post-link optimization I built with Dr. Tim Jones at the University of Cambridge. Why build a post-link optimizer, and why build one for OCaml in particular? OCaml is a high-level language, which means that it is not well suited for expressing specific low-level constructs. As an example, we consider a simple type to represent complex numbers composed of an imaginary and a real component. If we declare a complex number as a pair of floats, we end up with many allocations. Even though we only care about 8 bytes of data to store two 32-bit floats, the object will be spread across 56 bytes and 3 distinct allocations, producing 3 distinct blocks on the heap. Ideally, we like a single block with a header and 8 bytes of data. So how do we get there? We can write a lot of code, possibly fiddling with bits, and express the type in OCaml. However, the solution is unlikely to be elegant. We could also change the runtime or the compiler. However, this is not practical nor scalable and could become a maintenance nightmare. We choose to instead use an existing language feature, namely the foreign function interface. The FFI allows us to use the right tool for the right job. We can express low-level constructs in C and call them from OCaml. The FFI of OCaml is particularly powerful thanks to its minimal runtime and simple object representation. This allows us to read arbitrary objects from the OCaml heap and also to allocate arbitrary objects on the OCaml heap. Such features allow the FFI to be flexible enough to build a wide variety of types and functions. However, the FFI does not come for free. Besides the implicit trampolines and heap root management code required to invoke C from OCaml, we pay the cost of missed optimization opportunities. In a typical build, OCaml and C meet in assembly form in the linker. Unfortunately, high-level transformations of machine code are far from trivial. We need a common form more suitable for analysis. Ideally, a representation that has not yet gone through register allocation nor instruction selection. So, the goal of Duplo is to ameliorate this FFI overhead. And to reduce the overhead, we want to optimize across the language boundary. However, on one side we have OCaml and C on the other, two very different languages with different memory models and different runtimes. In order to apply any optimizations, we need to first find a common denominator capable of capturing the semantics of both C and OCaml. Duplo achieves this with a representation we call LLIR, Low-Level Intermediate Representation. The framework provides a custom version of Clang to lower C to LLIR, a custom version of the OCaml compiler to lower OCaml to LLIR, and an entire toolchain to link LLIR modules into a single module containing whole program information. And finally, an optimizer, which we call LLIR opt, to analyze and transform the program before lowering it to executable machine code. LLIR is the central component of our project. It is built to be easy to optimize. It is in SSA form, has virtual registers, simple instructions, and primitive types with direct hardware equivalents. Even though it is not LLVMIR, its in-memory representation in C++ is almost identical to LLVMIR, mirroring several useful methods and reusing support libraries, including valuable functions and iterators, such as dominator reconstruction and post-order reversals. We find the code style of our transformations to be quite similar to that of LLVM, and this familiarity is highly valuable. Despite some similarities, LLVM is definitely not LLVMIR. It is less abstract and a lot closer to hardware. Why is LLIR low level? This choice is almost entirely constrained by the OCaml compiler and the intermediate representations found in Clang. OCaml first compiles to lambda form with closures which have no direct equivalent in LLVM, require us to step one level down in the OCaml compiler. The next step is CMM, which still has some high-level features, so we need to go down another level. We are left with building LLIR from Mach linear, which are essentially equivalent to machine code. LLVMIR is more abstract than that. We need to lower it a bit in LLVM. Conveniently, we defined LLIR to be almost like machine code. We lower LLVM-IR to LLIR through the target-specific backend of LLVM, passing through selection DAG and LLIR-specific machine IR. On the OCaml side, we generate LLIR from linear, as the mapping is almost one-to-one. We are essentially cross-compiling to a new target in both compilers. Getting to LLIR is only the start of the journey. We also need to generate machine code from LLIR, and this step is non-trivial. Code generators tend to be complex pieces of code, and OCaml has the runtime and the garbage collector that we do not wish to alter that imposes further constraints. Since our toolchain already includes Clang, we decided to use the LLVM code generator from its selection DAG representation onwards. We have added a custom instruction required by the OCaml GC, using the entirety of the target-specific machine IR pipeline. Since we cross-compile C to LLIR, we have a mapping from selection DAG to LLIR. In our backend, we map LLIR to selection DAG. Due to this circular dependency, most of the LLIR instructions have a direct correspondent in selection DAG, with the exception of some more complex constructs such as function calls and 80-bit floats. Simpler instructions such as add, subtract, multiply, and so on do not really warrant a custom mapping from selection DAG to LLIR nor from LLIR to selection DAG. So we simply map selection DAG to an LLIR instruction and map the DLIR instruction back to selection DAG. But function calls are specific to each target, and even in all of LLVM's backends, they require custom mapping from LLVMIR to selection DAG, and we have that mapping for LLIR as well. And because of these constraints, we actually had very little freedom when designing our new representation. Probably the most pressing question is why not lower to LLVMIR? Previous attempts made some progress, albeit with the runtime cost. OCaml is not an easy language to map to LLVM. Its exception handling requires explicit stack manipulation. OCaml also lacks a shadow stack for root pointers. This aspect is crucial for performance. While LLVM offers some support for garbage collectors, it does not cater specifically to the needs of OCaml. Through Duplo, we made significant progress though. We have added the required instruction to a significant portion of the target specific pipeline in order to handle the frame tables used by the default OCaml garbage collector and runtime. However, to achieve the same at the LLVM IR level, extensive changes are required. To illustrate LLIR, we can look at a simple method in LLIR form, which computes the magnitude of a vector allocated on the OCaml heap. It reads an argument, a pointer to a pair, using an arg instruction. Individual elements are loaded using LD from offsets computed using basic pointer arithmetic. The elements are squared using the multiply instruction, then passed on to the square root function before being boxed into a heap allocated block. We can notice the annotations. The OCaml runtime requires us to identify all heap pointers, which we do using camel value, and emit frame tables describing those which are live across call size that can allocate, all marked through camel frame. Finding a common representation is only part of the problem. In this representation, optimizations opportunities to perform optimizations should be scarce. OCaml should have already optimized everything. LLVM should have also optimized everything. And we are left with the non-trivial task of identifying optimization opportunities that are exposed only when both OCaml and C sources are present. Naturally, the first step is to create optimization opportunities for other steps. Inlining achieves this. Unfortunately, inlining in this context is not as simple as copying a body into a callee. The world is split into two realms, OCaml and C. The two communicate through a trampoline, recording vital information for the runtime. When we inline C into OCaml, we actually create a bigger OCaml function and push the trampolines down. Even though G initially called F without a trampoline, after inlining it requires one. H cannot allocate, thus it does not need one. In camel FF, we are left with a mess. The function now tracks heap roots using both camel values and an explicit root management mechanism specific to C. In the future, we aim to address this problem by moving roots over to the camel value mechanism. This is a great improvement since it eliminates the upfront cost of root management that's necessary in C. As you have global information, in the future we will also be able to move C functions which allocate over to the OCaml realm, further simplifying manual root management and possibly ending up only using camel value annotations to identify roots. While we are not there yet, at some point we will be able to not care about whether a function is OCaml specific or C specific, erasing the boundary between the two heaps. To illustrate some more problems, we consider a function that increments a double, unboxing a value, adding one to it, and boxing it back, sending it back to the OCaml heap. After inlining, we see that the boxing camel copy double call is now annotated and it has a trampoline. But what happens if we inline two consecutive invocations? Unfortunately, we get a chain of boxing unboxing steps. This is expected and quite unfortunate. We are now faced with the non-trivial task of understanding pointers and blocks on the heap to perform even a simple transformation such as constant propagation. And the stage we are at in the pipeline does not help. The common ground between C and OCaml memory representations is not particularly verbose. We can work only with the assumption that pointers are stored at addresses aligned to 8 bytes. We essentially have no type information. And even if we had type information, due to the fact that C has unions, the type information we could possibly keep would be minimal, and the only piece of information we'll be left with is this fact that pointers are aligned to 8 bytes, which allows us to model the heap as bags of pointers aligned at specific addresses. As a proof of concept, we have built two transformations working with pointers. A local analysis to propagate values stored to memory to loads reading them, and a global analysis to identify indirect call targets essential for that code elimination. Presently, our optimizer implements a number of classic transformations, which are required mostly to eliminate inefficiencies in the C OCaml LLIR lowering. While we have exposed many new opportunities, our goal for the moment was to implement the minimal battery of transformations required to emit code as fast as, well, at least as fast as it was emitted by OCaml and C previously. Our transformations include sparse conditional constant propagation, unreachable code elimination, and control flow simplification. And these are scheduled after inlining and simplify the program quite a bit. Their recursion elimination is vital. LLVM cannot lower direct air recursion as effectively as OCaml, but it generates identical code if these functions are turned into loops instead. An interesting transformation specific to this context is trampoline elimination. OCaml requires a trampoline to switch from the OCaml calling convention to the C calling convention when invoking a C method indirectly. Since you have global information, we can change the calling convention of the C method to the OCaml one, completely eliminating these trampolines. These transformations, along with the LLVM code generator, provide some benefit. We benchmarked our optimizer on a subset of benchmark from OPERF macro and OPERF micro. Unfortunately, we do not yet implement some optimizations performed by the OCaml compiler, which we have disabled in our reference version. We do not cache some globals in registers, and we do not inline allocations. Despite these mitigations, the relative results should still be relevant. Our linker delivers a significant reduction in code size, while LLVM manages to select better instructions, providing some improvement on large informations, and we're quite happy about these results. When comparing the effect of the small set of transformations we have implemented, the effect is moderate. There are not many opportunities for cross-language optimization, as our inlining heuristics and poist analysis are quite primitive. As an example, we currently inline aggressively functions which box or deconstruct arguments in the hope of propagating constants through them. In the future, we have to build better heuristics to base our inline decision on. However, for the purpose of this project, the difficulty was in figuring out how to do inlining in the first place. We do gain in performance a bit by mitigating inefficiencies in both backends and inlining some small methods through the battery of transformations we have presented earlier. To sum up, we have presented the Duplo framework to inline C into OCaml, analyzing and transforming the resulting code. We built a new representation to capture both OCaml and C, and which we call LLIR. Finally, as our code generator, we have shown how OCaml can be lowered to part of the LLVM pipeline, yielding an improvement in code size and performance.
Thanks very much, Nandor, who's now available in the New York time band for question and answer. You can click the link in Clouder. Now we have Vikram Chowdhury discussing how to embed purity in an impure language via the use of a comonad.
Hello, I'm Vikram Chowdhury, and I'm going to be presenting some joint work with Neil Krishnaswamy on our paper, Recovering Purity with Comonads and Capabilities. The basic problem in this paper is the following. We've known for a while now how to extend a purely functional language with monads to encode side effects. However, what if we already have an impure functional language? Can we extend the type system to encode the absence of effects? So let's try to motivate why such a thing might be useful with some examples. Consider a strict call-by-value language which allows side effects, and let's consider the map functional. So map is a higher order function which takes a function f and applies it to every element of the list recursively. There are at least two different ways of writing map. In map1, we recursively call map1 on the tail of the list before evaluating f on the head of the list. In map2, we evaluate f on the head of the list before recursively calling map2 on the tail of the list. So these two functions should be equal, but in an impure language like this, they can have different side effects. So as an example, let's evaluate map1 and map2 on the following inputs. So here f is the identity function on strings, but it's impure. It prints its input string to standard out before returning it. So let's try to reduce map1. We expand the let, and we observe that it reaches the end of the list when it tries to evaluate f on the string right. So this prints right. Reducing more, we see that it calls f on 2, which prints 2. And then it calls f on left, which prints left. And finally, it returns the original list. So it produced a side effect where it printed right to left. If, however, we reduce map2 on the same inputs, we notice that it evaluates f first on the string left, then on the string 2, and then on right, and finally returns the original list. So even though both of these map functions return the same output, they produce different side effects. Alternatively, consider these two functions f and g from int to int. They perform different side effects before returning their output. Now, suppose we mapped g on xs, followed by mapping f on the output. An optimizing compiler could perform map fusion on this expression. But in this impure language, if we mapped f compose g on xs, that would produce a different side effect. So this map fusion optimization pass would be invalid. So I hope these examples are motivating, and they show that it would indeed be useful to be able to encode the absence of effects in an impure language. So first, let's see how effects are being encoded in this language with some examples. Let's consider this function g. It takes the channel C, a string S, prints S on the channel C, then returns S. So this function is impure because it uses the channel it was passed to perform an effect. Now consider this function f from string to string. This is also impure, but it is defined by partially applying g to standard out. Now, standard out is a channel that's available in the global environment. So there is a difference between f and g. G is safe because it uses the channel that was passed as an argument, but F uses standard out, which is used from the global environment. So this gives us an idea. We should be able to control the use of effects by controlling the channel variables that a function has access to in its environment. So we were interested in purity, but we can refine this to a different notion of safety. So we formalize this idea using the notion of capabilities. So capabilities are a well-known thing in the systems programming community. A capability is defined to be a token of authority. For example, a security token or a permission. In our impure language, a channel variable, for example, standard out, is a capability. Then we define the notion of capability safety. We say that a program is capability safe when it only performs effects using the capabilities it has access to at runtime. So for example, this function G is capability safe, but F is not. But G is not pure, it's only safe. So we'll come back to how we could encode purity using safety. But for now, let's try to extend our language with safety. So first, we want to distinguish between two kinds of variables, safe variables and impure variables. Safe variables are capability safe, and impure variables are just arbitrary variables in our language. So we use these qualifiers, S or I, in blue and red, to annotate the bindings of variables in our context. Then we would like to internalize the notion of safety using a safe type constructor. We add a box type constructor, and we add two new term formers, box and letbox. So these are expressions, and we distinguish between expressions and values. Boxing an expression turns it into a value. We also have a new safety judgment, which we use to judge whether a term E of type A is safe in context gamma. So now we want to ensure that safe variables can only depend on other safe variables. So we add a substructural operation on our contexts. So this purify operation drops all the impure variables in our context. Then, if we know that a term is well typed in a safe context, we know that it's safe. And if we know that a term is safe, we can put it inside the box using our box introduction rule. And finally, we also have a letbox elimination rule for our box type constructor. So if E1 is a boxed term, we can bind the underlying value x, and we can eliminate to E2 if it is well typed in the extended context, where x is marked with a safe annotation. So these were the additional typing rules for the box type. Let's also take a quick look at the other typing rules. The rule for variables remains essentially unchanged. For functions, to introduce a lambda, we allow the bound variable to be impure, so that we can substitute arbitrary expressions. The lambda application rule remains the same. And then finally, the rule for print is just as expected. It's simply a unit. Now, at this point, we note that this box constructor is a comonad. It has a co-unit and it has a co-multiplication. And in fact, our syntax for adding comonads to our type theory is inspired by the classic Fenning-Davis paper on the judgmental reconstruction of S4 modal logic. Instead of dual contexts, we use annotations on our variables. And for more details on the syntax, see our paper. So coming back to our original motivation, can we use this notion of safety to recover purity? Well, we say that a function is pure if it is safe and it has access to zero capabilities in its environment. So box of A arrow B is the type of safe functions, but they're not necessarily pure. And box of A arrow B is the type of pure functions. So going back to our original example, we can now write a pure variant of our map2 and map1 and map2 functions. We force the function argument to be pure, and it should be only applied to a list of safe expressions. We can use box and let box to rewrite the body of map1 and map2. So using this new definition for map1 and map2, we can show that they are provably equal in the extended calculus. Finally, to conclude, let me point out some of the main takeaways from this talk. First, we can use this notion of capabilities to encode effects and to control the usage of effects. This idea of capability safety, or denying the usage of a capability from the environment, can be captured using a comonadic type discipline. Let me also highlight some of the technical results in our paper. We formalize an effectful calculus and we extend it with a safety modality. And we show how to do substitution and so on. We show how to recover purity from capability safety. And we also discuss how to do capability taming, that is, how to incrementally add safety to an already impure language or a library. We give a categorical semantics for this language. It is given by a Cartesian closed category with a monad and a comonad, which interact with each other. We give a construction of capability spaces, which give us a denotational semantics, which satisfies the axiomatic categorical structure that we need for our semantics. The idea of this construction, in fact, comes from an old paper of Martin Hoffman. Also, capability spaces have more structure than we actually use for our semantics. It can be used to give a model of linear type theory, which we discuss in the paper. We also give the full equational theory for this calculus, and we use our denotational semantics to prove its soundness. Finally, we also show how to embed the pure simply typed lambda calculus into our language using this comonadic modality. This embedding preserves the equational theory of the pure STLC. Also, we show that our language is a conservative extension of the STLC. This is a requirement for a purely functional language that Amr Sabri told us about a long time ago. And yeah, that's all I had to say. Please see the extended version of our paper if you're interested. And thank you very much for listening.
Thanks, Vikraman. He is now available in both the New York and Asia time bands for question and answer. We'll take a brief pause for the next talk at 12:15 in the New York time band. Next up, We have Xiaoheng Chen to present a general approach to define binders using matching logic.
Hello everyone, welcome to this video. My name is Xiaoheng Chen. My talk today is about a general approach to define binders using matching logic. This is a joint work with my supervisor, Professor Grigory Rasu. Our papers can be found at the links below. The technical report includes all the proof details in the appendix. The main motivation of the work is the K formal semantic framework and its logical foundation, matching logic. The K framework allows users to define the formal semantics of any programming languages. As shown in the picture, once the semantics is defined, all language tools such as parsers, interpreters, and verifiers are automatically generated by K. In practice, K has been used to define the formal semantics of many real-world languages such as C, Java, and JavaScript. K allows users to define the common language features easily, including binders. For example, the following K definition defines the syntax of lambda calculus. An expression is either a variable or an expression applied to another expression, or has the form lambda x lambda var.e. The binder is an attribute which will trigger the internal substitution mechanism in K to provide a correct implementation of capture volume substitution. Currently, this only works for a restricted form of binders, but with this paper, we can give the binder attribute a clean mathematical explanation, which will make K to support more general binders in the future. Mathematically speaking, every K definition is a logical theory of matching logic, where the syntax and semantics of a programming language are defined using matching logic axioms. So our job in this paper is to show how to define binders as matching logic theories. Matching logic is expressive. Many important logical systems can be defined as matching logic theories. These include first logic, separation logic, Hall logic for program verification, temporal logics, and many others. However, no logical systems where binding plays a major role have been thoroughly defined in matching logic until this paper. In this paper, we study the typical systems that include binders, such as lambda calculus and type systems. We define them as matching logic theories, and we prove that our definitions are correct by showing that they preserve the syntax, semantics, and formal reasoning of the target system. Here is an overview of the main contribution of the paper. Firstly, we simplify matching logic and propose a variant that is more suitable to define binders. Secondly, we use lambda calculus as an example and define it as a matching logic theory, gamma lambda. The key observation is that lambda xe does two things at a time. It creates the binding of x in E and also builds a term lambda xe. In matching logic, we separate these two. We first use bracket xe to define the graph of the function that maps x to E. Here, xe is the pair of x and E, and in matching logic, exists means union. So this pattern is the set of all pairs xe, where x ranges over the variables. The intension packs the graph set into one element, which then includes all the binding information. Then we define lambda xe by applying the constructor lambda to the graph set xe. The constructor builds the term. In short, we use the built-in exists binder of matching logic to build a graph set and create a binding, and then use constructors to build the term. To show that the above definitions is indeed correct, we prove the following theorems. We prove that gamma lambda is a conservative extension of lambda calculus, so any equations between two lambda expressions are provable in lambda calculus if and only if they are provable in the theory gamma lambda. We also show that gamma lambda is sound and complete, so semantic validity and provability coincide. One important advantage of our approach is that the theory gamma lambda automatically gives a class of matching logic models, and the following two theorems connect those models to lambda calculus. The representative completeness states that for any lambda theory, T, which is a set of lambda equations, there is a model MT of theory gamma lambda, such that MT captures precisely the lambda theory T. That is, E1 equals E2 is provable in T if and only if it holds in MT. The last theorem states that for any lambda calculus model A, there is a matching logic model MA of the theory gamma lambda that captures A. Lambda calculus has many different models. In this paper, we consider the models that are concrete Cartesian closed categories, or called concrete CCC models. The technical details can be found in the paper. To sum up, our definition of lambda calculus that first creates the binding and then builds the term is correct and captures lambda calculus faithfully. Then at the end of the paper, we generalize it to other systems with binders, such as system math, pure type systems, etc. In the following, I'll give a high-level overview of matching logic, including its syntax, semantics, and then, as an example, I'll define lambda calculus in matching logic. Due to time limit, I won't discuss the generalization part in this talk, but I'll be happy to address it in the Q&A session. Matching logic is a very simple and minimal and yet expressive logic. It is the logical foundation of the K framework. Its syntax defines formulas, which we call patterns, using only 7 constructs. They are element variables, which are like first logic variables that range over elements, set variables, which are like propositional variables in modal logic that range over subsets. Symbols are like set variables, except that their interpretations are fixed by the models and do not change. Phi1, Phi2 is the application pattern, where we apply Phi1 to Phi2. If Phi1 is a function or a constructor, then the result is like a first logic term. If Phi1 is a predicate, then the result is like a first logic atomic formula. But in general, any pattern can be applied to any other pattern, giving matching logic maximum flexibility. Next two constructs, bottom and implication, are standard propositional constraints. Other propositional operations can be defined from these two. Finally, exists X phi builds the existential quantification like in first logic. Now we move on to the semantics. The semantics of matching logic is one sentence. A pattern phi is interpreted as the set of elements that match it. In other words, patterns mean sets. Formally, a model M has a non-empty carrier set and a binary application function from M to the power set of M, which will be used to interpret the application pattern. Each symbol is also interpreted as a subset of M. Now, given a valuation that assigns element variables to elements and set variables to sets, the pattern interpretation phi rho is defined like this. For example, X evaluates the element role of X, sigma evaluates to the interpretation sigma n, bottom evaluates to the empty set, meaning that no elements can match it. Application is interpreted using the application function. But now, phi1 and phi2 are also sets. We range over their inhabitants by A1 and A2 and take the union of all the results. This is called the pointwise extension. Finally, exists X phi is interpreted by ranging over all elements A in M and taking the big union of all the resulting sets. In short, exists means big union in matching logic. In matching logic, we use theories to capture the target logical system, such as lambda calculus. A theory consists of two components, a set of symbols and a set of axioms that define the behavior of the symbols. We also define notations, which are just syntactic sugar. With the proper notations, we can capture the formulas or expressions in the target system as is without any translation. We say that a model M is a model of the theory gamma if all axioms hold in the model. That is, they are interpreted to the total set. Then, for each theory, we have a class of its models whose properties can be expressed by patterns. For gamma to correctly capture the target system, we need to establish an equivalence between the models of gamma and the models of the target system. Then we can use matching logic patterns to express and reason about the properties about the target system. In section 4 of the paper, we define the matching logic theories that captures many important mathematical concepts, such as equality, membership, the concept of sorts and many sorted functions, pairs, and the power sort 2 to the s, whose elements are the sets of elements of sort s. Based on these infrastructure definitions, we now define binders in matching logic. We define the theory gamma lambda that captures lambda calculus. Due to time limit, I only show the intuitive ideas. Intuitively, the lambda abstraction lambda xe creates infinitely many alpha equivalent representations. Lambda x1e, x1 substitute for x, etc. Our idea is to capture these representations. To do that, we construct an argument value pair where the first argument is the variable and the second is the substituted expression. Then we define this existential pattern. Recall that the semantics of existing matching logic means set union. So this pattern means the union of all pairs. In other words, this pattern is the graph of the function that maps x into E. To wrap up the definition, we take the intension of the graph set. The intension of the set equals to the set itself, but the set is no longer regarded as a collection of elements, but as a single element in the power set domain. This way, we can avoid the pointwise extension when we apply the constructor lambda to the set. We introduce the notation bracket xe to mean the intension of the graph set, which is one element that encodes all the binding information of x into E. And finally, we define lambda xe as the application pattern where the constructor lambda is applied to the graph set bracket xe. In short, to define lambda abstraction, we first use the built-in binder exists to define the graph set and capture the binding behavior. Then we build the lambda term using the constructor and the matching logic application. The correctness of the definition means that the encoding from lambda calculus to matching logic is faithful with respect to the syntax, semantics, and the formal reasoning of lambda calculus. In terms of the syntax, matching logic captures lambda expressions verbatim. The lambda abstraction becomes this pattern, where we use lambda to build a term and use bracket xe, which is the graph set, to build the binding. In lambda calculus, formal reasoning means equational reasoning plus the beta reduction rule. To capture that, we add beta reduction as an axiom schema to the theory lambda. Then we can prove that gamma lambda indeed captures lambda calculus faithfully, in the sense that lambda calculus reasoning is equivalent to the matching logic formal reasoning within the theory gamma lambda, and is also equivalent to the semantic validity within the theory gamma lambda. To conclude, in this paper, we gave a generic way to dealing with binding using matching logic. Since matching logic is the logical foundation of K, our work is useful to the development of K. In the paper, we propose a simple matching logic variant that has only 7 syntactic constructs, and we fully develop its model and proof theories. Then we define the matching logic theory for lambda calculus, where lambda abstraction is defined by applying the constructor lambda to the graph set bracket xe. We prove the correctness of this definition by showing the equivalence among the validity and the provability of lambda calculus and matching logic. Finally, we extended our approach to all binders in a systematic way, where the details can be found in the paper. Due to the time limit, I cannot fully cover all technical details in this talk. The paper and the companion technical report contain all the details. I'm happy to answer any questions about the work in the Q&A session. Thank you for watching.
Thanks very much, Xiaohong, who is now available in both the New York and Asia time bands for question and answer. Next up, we have Piers Dara presenting Parsing with Zippers, a functional Perl.
Hello, thank you for watching my talk. My name is Piers Dara, and I'll be walking you through Parsing with Zippers, a functional Perl written by Michael D. Adams and me. So let's get to it. Parsing with Zippers is an extension of the earlier work of Parsing with Derivatives, which we'll call PWD for short. We address an underlying inefficiency in PWD's algorithm by implementing a new, generalized form of the zipper and using it to manage derivations. Our resulting algorithm is significantly faster than the original PWD implementation, measurably faster than the optimized PWD implementation of Adams et al. 2015, and is only around 100 lines of OCaml code when fully implemented. The primary contribution of Parsing with Derivatives was to generalize Brzezowski's derivatives from regular expressions to context-free grammars. This is not trivial. The Brzezowski derivative uses two eager algorithms, perfectly fine for regular languages, but not so with CFGs, which have recursion. PWD introduced laziness to fix most of one of those algorithms, and memoization and fixed points for the other. The result is an algorithm that is elegant in its theoretical simplicity, and which can also produce full parse trees instead of only recognizing inputs, as Brzezowski's derivatives do. Let's see a brief example of PWD in action. We start with a grammar consisting of a root concatenation node, shown with the circle-like concatenation operator, that has two children concatenation nodes, each of which has two children token nodes. This grammar parses only the string A, B, C, D. We will attempt to parse that string, shown disassembled in the tokens at the top. We take the first token from the input string, labeling it current. Then we derive over the grammar, beginning at the root node. At each step, a pattern match is run to determine what to do with the current node. The derivative proceeds down the left side of each concatenation node as it attempts to find a token node. Eventually, it finds the first token node, A. When the algorithm comes to a token node, it attempts to match that token to the current token that we are taking the derivative of the grammar with respect to, in this case, also A. Because the tokens match, we replace the token grammar expression with a lambda, indicating a successful parse. Since we have successfully derived the grammar with respect to A, let's proceed and attempt to derive the result with respect to B. Again, we begin our search at the root of the grammar, exploring each node in sequence until we find an unmatched token node. And in this case, the traversal down to the lambda would be thrown away, so I'm only showing the traversal down towards the B node. Because the current token and the found token node matched, we replace the node with a lambda node and return a new grammar. We'll stop the parsing example at this point. The takeaway is that each derivative will start at the root of the previous derivative's result grammar. In this simple example, this only means one extra step, but with a more complex grammar with many layers, it can be very many steps. This is wasted effort. Most often, subsequent derivatives need to essentially resume from wherever the previous derivative left off. The PWD algorithm does not account for this, and so it spends a lot of time on redundant traversals. To avoid this, we'll employ the zipper. The zipper is a functional data structure for navigating trees introduced by Hewitt in 1997. We start with a simple definition for a tree data type consisting of either an item, which is a leaf node, or a section, which is a branch. Next, we introduce the path. A path is essentially a context. It represents the part of the tree which has already been traversed and also keeps track of siblings of the subtree currently being focused on. Last, we have the location, which is really the zipper itself. This is a pair of a path with the focused on subtree, which is generally referred to as the focus of the zipper. To solidify this concept, let's look at a visualization. In this diagram, blue squares represent paths, yellow triangles represent tree nodes, and the red circle is a zipper. The red arrow going down from the zipper is the focus expression, and the black arrow going up points to the path. Let's take a few steps through the tree. We'll begin by going down through the subtree T1. When we go down into a concatenation node, a new node path will be created representing the path back up through that concatenation node. This will be attached to the zipper, which will be focused on the first child of the concatenation node, T2 in this case. The remaining children, T3 and T4, are in the node path's right siblings list. We are not limited to traversing the tree in a specific order. We can immediately move to the right without going in any other direction. Notice that a new node path is constructed, which has T2 as a left sibling of the focus and T4 as a right sibling. If we go down through T3, we will create a new node path, C3, which itself points up to C2. Because T3 had no siblings, the left and right sibling lists in C3 are left empty. Lastly, we can return back up through a path, in this case, C3. When we do this, we could create a new node to replace T3, which is why I've underlined T3 in the diagram at this point. In any case, a new zipper is constructed focusing on the tree node we just traveled through, with a path back to the root as always. This brings us to parsing with zippers, or PWZ for short. We use zippers to save the location where a derivative was successfully taken. By doing this, we eliminate almost all of the retraversals in the original parsing with derivatives algorithm. We use a slightly modified zipper definition compared to the original. For one, we actually call it a zipper in the code instead of a location. We also rename tree to exp, meaning grammar expressions, and path to cxt, meaning contexts. All context constructors end with a capital C to indicate their status. Now, there is a problem with our zipper implementation, which is this. It can't yet handle all context-free grammars. It'll work fine for concatenation and tokens, but that's it. Many CFGs have alternates and cycles, which are part of what makes CFGs so useful. We'll have to improve our zipper if we want to use it for parsing CFGs. First, we'll look at supporting alternates in the grammar. This requires adding an alternate constructor to the exp type, and a corresponding alternate context constructor to the cxt type. Here, we have a simple grammar. The inverted triangle labeled A1 is an alternate node, and T1 and T2 are its children. They should be processed independently of one another. When the zipper moves through the alternate node A1, it splits. We get 2 context nodes and 2 zippers, which is exactly what we wanted. Now the children of an alternate node are handled in a non-deterministic manner. When we eventually traverse back up, possibly modifying either or both of the child nodes in the process, we create a new alternate node for each child. These are handled independently by the algorithm. For non-cyclic grammars, this solution is technically sufficient. However, there are some inefficiencies. Here we have a situation where 3 expressions have been parsed, which all descend to a shared expression T1. There are 3 separate zippers sitting between each of the associated context and this T1 expression. Parsing with the first zipper creates a new context, C4, and a new zipper, Z4, which sits between the new context and the child expression T2. Parsing with the second zipper creates an identical context and zipper, but they are separate from the first ones, and the third zipper will do the same. We now have 3 identical contexts, all labeled C4, and 3 identical zippers, all labeled Z4. This is wasted effort. Not only that, but if we were to add support for cycles at this point, the inefficiency could compound and lead to the number of zippers becoming exponential with respect to the length of the input. We can't have that. Here's the code as we currently have it, but now we'll add memoization. The memoization entries simply take the place of the child contexts within each context type, as well as within the zipper. We now have a memoization table, shown on the left. Although the zippers now actually point upward to memoization entries, I show them here pointing to the associated context for visual simplicity. When zipper Z1 attempts to parse into expression T1, we will add an entry to the memoization table so subsequent derivations do not repeat work. It's important that the table entry is added before descending, or else we may still end up with redundant traversals. When the first zipper, Z1, descends through the expression T1, a new entry is added to the memoization table indexed by a pair consisting of the current input token position, which we will call P here, and the expression. The zipper's context, C1, is added to the parents field. When the derivative is complete, the result field will be populated, and we will continue parsing upwards through the parents. Now, when zipper Z2 attempts to parse through expression T1, it first checks the memoization table. If the current input token position is still P, then the lookup in the table will succeed. Instead of doing any additional processing, Z2 will simply add its current context, C2, to the parents field. The last zipper, Z3, will do the same. When the child zipper Z4 eventually returns from parsing through the T2 expression and ascends up through the context C4, it will split again to return the computed result to each of the parent contexts C1, C2, and C3. By using this memoization table, we have avoided creating redundant zippers when traversing down the grammar. But what happens when we instead traverse up? Here's an example where a zipper is focused on an alternate which has not been parsed yet, so it has no entry in the memoization table. The way the algorithm works at this point causes 2 new zippers to be spawned, each pointing to a new Alt-C context node. Note that both contexts, C2 and C3, point to the same memoization table entry for the A1 alternate expression that we just passed through. Let's say zipper Z2 does its work first and returns up through context C2. A new alt node is constructed, A2. This is added to the result field of the old alternate node A1's memoization table entry. When the second child zipper, Z3, passes up through context C3, it also creates a new alt node, A3. This node is also added to A1's result field. 2 alternate nodes have been created, and each has spawned a zipper that will navigate up through the parent context C1. This is inefficient, and, similar to the problem with unshared expressions, this situation can lead to an exponential blowup in the number of zippers spawned when deriving over a cyclic grammar. To address this, we will adjust our memoization code to also memoize contexts in addition to expressions. Because the situation only arises for alternate nodes, we simply extend the alt constructor to have a mutable list of child expressions. This will allow us to incrementally update a constructed alt node's list of children as new zippers return up through the tree. We also now only need a single expression to be saved in the result field of the memoization entry. Let's see how it works. We start back at this point, where a zipper has just passed up through an alt-C alternate context and created a new alternate node, A2. The node is added as the lone result in the memoization table. When the second zipper moves up in the tree, it simply modifies the existing A2 node. Now, there is only one zipper created above the newly constructed alternate node, and we have avoided the potential exponential behavior we would have had earlier. While adding memoization to reduce inefficiencies, I mentioned some concerns about a hypothetical future where we support cyclic grammars. Have no fear, the time has come to handle cycles. And behold, they are handled already. Where recursive descent parsers face a dilemma in choosing how many times to descend into a left recursion, we sidestep the issue entirely. Our memoization strategy automatically converts cycles in the grammar into cycles in the contexts. This allows us to postpone making any choices until further parsing reveals how many repetitions are actually needed. The diagramming for this is a bit complex, so I suggest reading section 7 of our paper for a more detailed explanation. And with that, the fundamental theory of our algorithm is laid out, but there remains one more advancement to discuss prior to looking at the evaluation. We can actually completely eliminate the memoization tables, and I'll show why. All our memoizations are indexed by the current input position, but we parse the input tokens sequentially, so there is never a need to maintain old entries. We eliminate the position as an index, and instead make two fields in the table entry to denote the start and end positions corresponding to the successful parse. However, since this table is now indexed only by an expression, we can actually eliminate it entirely and simply put a memoization entry inside each expression automatically. Here's the code as it existed with the memoization table. And here is the code which eliminates memoization tables. We now have a new definition of exp which contains a memoization record, and an exp prime, which was previously called exp. The memoization entries now record the start and end positions associated with successful parses, allowing the algorithm to quickly discern whether an entry has grown stale. And with that, the work is done. Let's briefly look at our performance evaluation. We ran parsing with zippers over the Python 3.4.3 standard library and compared the results to a few other parsers. Parsing with derivatives from Might et al. 2011, optimized parsing with derivatives from Adams et al. 2016, Menhir, an LRK parser generator for OCaml, and Dipgen, a GLR parser generator for OCaml. The parsing with derivatives implementations had to be ported from Racket to OCaml, and Menhir's LRK limitations required that we reformulate some of the Python grammar to avoid potential ambiguities that might distort our comparisons. We ran the benchmarks on a DigitalOcean droplet with a dedicated CPU to ensure we did not introduce any sources of invalidity due to other tasks. The results show that parsing with zippers significantly outperforms the original parsing with derivatives algorithm, and even outperforms the optimized version of PWD that relies on many low-level tunings and adjustments to the algorithm. Although PWZ does not surpass the parser generators in our tests, we believe our result to be significant because of the simplicity of the algorithm. At only around 100 lines of code, parsing with zippers is simple enough to be written by hand, and yet is fairly competitive as long as performance is not absolutely crucial. Additionally, we claim parsing with zippers can handle all context-free grammars, even with left recursion and ambiguities, which Menhir cannot do. So, we've introduced parsing with zippers, a new general parsing algorithm that is simple to implement yet provides surprisingly good performance. Where parsing with derivatives generalize the Brzezowski derivative from regular expressions to context-free grammars, we have generalized the zipper from tree structures to context-free grammars. We also consider asymptotic complexity, other divergences from PWD, and a few more points in the discussion and evaluation sections of the paper, which I would encourage you to read if you have further questions that I did not address. I hope you have enjoyed this presentation of Parsing with Zippers, a functional Perl by Pierce Dara, that's me, and Michael D. Adams. Please feel free to contact us if you have any additional questions or comments. Thank you.
Thanks very much, Pierce. In the New York time band, the authors are now available for question and answer. I'm afraid not in the Asia time band. Okay, last up in this session, we have Timothée Odeberg presenting regular language type inference with term rewriting.
Hello everyone, my name is Timothée Odeberg, and in this presentation I will be talking about our latest work on the automatic verification of higher order functional programs, where we designed a regular language type inference system using term rewriting. This is a joint work with Thomas Genet and Thomas Jensen at the French Institute for Research in Computer Science. And the technique that we have developed is dedicated to the fully automatic verification of higher order functional program processing algebraic data types. What you see on this slide is an example of what we want to achieve. On the left side is the user input. It is a higher order functional program written for the purpose of the presentation in OCaml. It defines a recursive function, sort, that implements the insertion sort algorithm, taking as parameter the comparison function, and also a sorted predicate that verifies that the list is indeed sorted according to the same input comparison function. The right side shows that we imagine could be the user interface. Here the user can type in the property he wants to verify. So here, for example, we want to verify that for all list L, the output of the sort function is indeed sorted according to the corresponding predicate. Note that the property uses predicates that are defined in the program, and without any more information, without annotation, we are able to check if the property is verified or find a counter example. If the property cannot be verified with a regular abstraction of the program, it will diverge. To understand why our contribution was necessary and how it relates to other higher order functional program verification techniques, I like to place every technique on this diagram. Many properties can be verified by simplifying or abstracting the behavior of the input program in a certain way. So we can classify verification techniques according to the abstraction they can generate. On the bottom, we put techniques that can verify properties with any regular abstraction. On the top, we put techniques that can verify property with any abstraction. Overall, this axis measures the range of properties that can be verified by the technique. From left to right, we measure how much a user is active during the verification. On the left, we have fully automated techniques, and on the right, manual techniques. Proof assistants such as Coq or Isabelle HOL can be placed in this region. They can verify a large range of properties, but require a lot of manual work. Refinement types inference techniques, which can be seen in liquid types or F-star, require less manual work. The user only needs to give some hints, usually as program type annotation. However, the range of verifiable properties is reduced. Fully automated techniques have been developed around higher order model checking, predicate abstraction, and more. These techniques do not require any annotations, but mainly focus on relational properties over numerical data types, and are generally not good at verifying regular properties over algebraic data types. There have been some attempts in the fully automatic verification of regular properties, including our previous work teambook. However, these techniques are incomplete and not scalable. In our paper, we propose a new technique that is complete on regular properties and modular to scale better. In our work, we use term rewriting systems to model programs and their semantics, and we use regular language of terms as types, which we are able to automatically infer using a regular invariant learning technique. Before I detail this type inference technique, let's start by an introduction of our theoretical frameworks: terms, language, and rewriting systems. A term is a labeled tree that we usually represent like this. It is composed of a symbol, f, living in a ranked alphabet, and n subterms, t1 to tn, where n is the arity of the symbol f. We call a pattern a term that has variable in it. Terms are useful to represent functional language expressions. This slide shows how OCaml expression can be translated into terms. Constants do not change, they have no subterms, unless it is a number, in which case we represent it by a tree using Peano's number representation. Functions application can be translated into a term where the arity of the symbol is the arity of the function, and subterms are parameters. However, this representation does not allow partial application of f, so instead we use the special @ symbol to represent a functional application, which takes the function and its first parameter. Control structures, such as the if then else, are simply represented as terms. Finally, let bindings and anonymous functions are erased, leaving only the bound body. Here, K. This is because the program's logic is preserved elsewhere as a term rewriting system. A term rewriting system defines a set of rewriting rules between patterns that encode the program's logic. Here is an example of the OCaml program defining the sorted predicate function on top, translated into a rewriting system on the bottom. Because there are a lot of function applications, you see a lot of @ symbols, which takes a lot of room and is hard to read. To simplify, we will write a space between the function and its parameters instead of @, just like this. Underline elements are the variables of the patterns. We see that each pattern matching rules on the top is translated into one or more rewriting rules on the bottom. Rewriting system can also be used to describe a regular language of terms as tree automata. Here is, for instance, on the right, the tree automaton recognizing every natural number, which can be used to partially represent the int type in OCaml. The rewriting rule defines that 0 rewrites into int because it is an int, and s of int, a successor, is also an int. In fact, tree automata can model any algebraic data type of OCaml. Here is the tree automaton for the following type of integer list. It defines two more rules for nil and cons that closely match the OCaml type definition. Tree automata can even represent regular languages that are not possible to define in OCaml. For instance, here is the tree automaton recognizing even numbers. This can be seen as the subtype of int. In our case, we call it a regular language type. Now that we are familiarized with rewriting systems and regular language types, let's dive into our verification technique. Remember that in our initial example, the user wants to verify that in his program for all list L, the output of sort L is sorted according to the corresponding predicate. In our verification settings, this problem is first translated into a rewriting problem. Here, it states that for all term L in the regular language of lists, and for all term V, if the input term rewrites into V, then V must be equal to true. In particular, it cannot be false. The list must be sorted. The arrow relation is defined by the term rewriting system translated from the input program. As we have seen earlier, regular languages can be seen as types. So we then translate our problem into a type-checking problem where we need to check that the following term is well-typed using regular language types. The overall target type is a regular language containing only the term true. Note that to check that, we will need to infer the appropriate intermediate type for sort L, since it is not given. From the partially typed given input term on the right, the type-checking algorithm is defined as follows. First, we extract a type signature for the topmost symbol, sorted. We know the expected output type, true. Constant values such as the comparison function, CMP, are typed with themselves and can be reported directly on the signature. We complete the blanks in the signature using our type inference procedure. We find that to output true, the input list must be sorted, which is represented by the regular language named sorted. We propagate back what we have found and check that it matches the initial type information, and then we repeat the same procedure with the subterm. Here we need to check sort L. We again extract a template signature for sort. Here we already have all the type information about sort, we just need to check it. The algorithm stops when all the types have been found or when a type error occurs when there is a contradiction. Of course, everything is built on top of our type inference procedure, which has been able to find the regular language of sorted lists. Let's see how this procedure works. The problem is as follows. As input, we have a rewriting system, a symbol F, and an output regular language type O. We want to find every input type A1 to AN such that every term F T1 to Tn is typed with O when each Ti is typed with AI. This can be summarized with the following abstract rewriting rule for F. For instance, let's consider the following rewriting system defining the recursive function even, deciding if a number is even or not. We want to know for which input regular language type this function returns true. So here our target output type contains only true. The expected output of the procedure is a partial abstraction of the input term rewriting system focusing on even that tells us that even returns true for every even number. The new type even is computed during the analysis. For recursive functions such as this one, the type inference is done using an invariant learning procedure. In our paper, we define a counterexample guided regular invariant learning procedure based on tree automata completion and SMT solving. It consists in repeating 4 steps until it finds a solution or a counterexample. Step 1, we experiment. We evaluate some terms of the form f of t1 to tn, where f is the analyzed symbol and t1 to tn some random input values. We do that efficiently using the tree automata completion algorithm. We then observe the result of our experiment and deduce some constraints on the language we are learning. We then make an hypothesis. By using an SMT solver, we solve the constraints, which generates an abstraction of the program execution. This gives us a possible regular language solution. We check the correctness of the abstraction by checking its completeness with regard to the rewriting system and the input domain. If it is, we are done, and if it isn't, we continue by doing more experiments. To illustrate the procedure, let's take back the even function example. First, we experiment with the values 0, 1, and 2 that are recognized in this automaton by the states x0, x1, x2. Using the tree automata completion, we know that even of 0 and even of 2 rewrites to true. This is encoded by the following rules. If we only use this information, then we cannot observe the constraints. Every tested value so far rewrites to true. As a consequence, if everything rewrites to true, then there is no point in separating x0 from x1 from x2. A solution to our empty constraint system is to merge them together into a new state tau0. By applying this substitution in the automaton, we get a candidate abstraction for our rewriting system where even applied to any number returns true. Of course, this does not pass the test. Every input value for even is represented, but some rewriting rules are not used. In particular, this abstraction misses the fact that even of 1 rewrites to false. So we cannot stop here. To continue, we add even of 1 in our experiment. It rewrites to false. This time, we observe that in order to separate true from false, we need to have x0 different from x2 and x1 different from x2. By solving this new constraint system, we make a new hypothesis in which x0 and x2 are equals, away from x1. If we look closely, we can notice that this new potential abstraction separates even and odd numbers, which is exactly what we want. And this time, every input value is represented, and every possible rewriting rule is used. So we can stop the analysis here. We have found an abstraction that gives us the correct input type for the output true, which is a new language even, recognizing even numbers. We have proved that this procedure is regularly complete, as it can learn any regular language, and complete in refutation. We have implemented it in OCaml in a new version of Teambook and tested it on more than 80 problems. When possible, we compare the performances with the previous version of Teambook. We thought that it is in average a second slower than Teambook 3, which can be explained by an overhead due to our typing facility. However, in the subset of problems on which we could compare, our implementation could handle 16% more problems without timing out. Surprisingly, the greatest improvement is in the memory usage, where in the worst case, Teambook 3 would consume several gigabytes of memory to solve some problems, where we never got past 40 megabytes. This is mostly due to our modular type system approach that allows us to split the problem into smaller parts. Thank you for listening, and don't hesitate to download the source code, which is available on our GitLab at the address below.
Okay, thanks Timothée, who is available in the New York time band for question and answer. We are now done with technical session number 5 of ICFP. In the New York time band, we have an ICFP coffee break coming up, and at 1:30, there's a virtualization feedback meeting with Benjamin Pierce, Jonathan Bell, and Krista Lopez coming up, so that's an exciting thing to join. In the Asia time band, in 1/2 hour, there will be a session on mentoring with Matthias Verleisen. Thanks very much, and I hope you enjoy the rest of ICFP.